3, 2, 1. Alright, here we go. A wonderful pre-recorded lecture. Alright, and last time we proved the rank nullity theorem, and today we'll talk about its consequences. So let's recall what the rank nullity theorem says. It says that if you give me an m by n matrix, then the rank plus the nullity being the dimension of the null space, and the rank being the dimension of the column space. Those two quantities must always add up to n, no matter what matrix you have. And note that they add up to the number of columns, the number of rows seemingly not playing a role, but as we talked about last time, we know that the rank is bounded above by the number of rows. So while it doesn't explicitly show up in the formula here, it is present. But anyway, so our method of proof for this theorem was to investigate the extremities of the nullity. The nullity, because the null space lives in Rn, we know that the nullity could not exceed n in terms of its dimension, and likewise the smallest possible value would be 0, and that was kind of the first step of proving this theorem, dealing with the cases of when the null space's dimension is 0, and when its dimension is n. And then the proof was, the main proof was, what happens if you're in the in-between cases, and we took care of that. But what we didn't do is really deal with the extremities of the rank. Well, we did see that rank of 0 can only happen if you've got the 0 matrix. So that's exciting. But we now want to see what happens when rank obtains one of these upper bounds. So note that rank here has to coincide with m or n as kind of one of its upper. It cannot exceed either value. It can't exceed the number of rows or the number of columns. Right. So our first task is to investigate what happens when rank hits one of these extreme values. And we'll see the rank nullity theorem tells us some interesting things about that. Alright, now, obviously, here we see that the value, the rank plus the nullity equal is the number of columns, so the rank hitting the number of columns is probably a bit more important than the rank hitting the number of rows, and indeed that is the case. A matrix is said to have a full rank if its rank is equal to the number of columns. We'll talk about the number of rows equaling the rank in a moment. Alright, but what happens when we're full rank? Well, then we are equivalent to the following three statements. Okay. So, full rank, note, implies that the columns are all linearly independent. And as we hopefully recall, the columns being linearly independent is equivalent to a bunch of other stuff, particularly the null space being trivial, and then in the case of a square matrix being invertible and being row equivalent to the identity matrix. So, hey, fun stuff. Alright, and what we'll also prove, and we sort of didn't explicitly note this, sort of implicit, but now we'll make it a bit more explicit, that any element of the column space has a unique x, so that a times x is equal to b. So in other words, a system that is consistent, so when ax equals b, that has a solution. That note means that b has to be in the column space. Not only is there a solution, but it is in fact unique. Ah, cool. Alright, so let's go for the proof of this pretty quick. Now, again, we've already pretty well trotted the linear independence of the columns. We know that's equivalent to the null space being trivial. So if we start off with full rank, well, then go to the rank nullity theorem, replace rank with n, then the n's cancel, and we get the dimension of the null space is 0, and that forces the null space to be trivial, which we see here, and we know that tells us the columns are linearly independent. Alright, now let's use the columns being linearly independent to show that the consistent systems must have unique solutions. Alright, so take an element of the column space, then we know that ax is equal to b for some x, so there is some solution. Now suppose you have another one. I'm going to verify that they have to be the same. Well, if ax is equal to b and ay is equal to b, then their difference has to equal 0. But their difference is a matrix multiplication, and we know that's really just a linear combination of the columns. And hey, we got a linear combo of the columns equaling 0. Well, we know then that all of the coefficients themselves must equal 0. And there we go, it's got to be that x is equal to y. Pretty cool. So, guaranteed the uniqueness. So, since you're in the column space, we know a element exists, and now with the columns being linearly independent, we get unique answers. All right, and let's close the loop now. We're doing the following are equivalent, so I need to show 1 implies 2, then 2 implies 3, and now we finish it off by showing that 3 implies 1. All right. Okay, well, suppose that for each element of the column space, we have a unique x, so that a times x is equal to b. So our systems, our consistent systems, have unique answers. All right, well, the homogeneous system is always consistent because it has the 0 vector as a solution, and now by hypothesis we know that can be the only solution, and thus the null space is trivial, so our dimension of our null space is 0, our nullity is 0, and by the rank nullity theorem, our nullity being 0 means that our rank is n. In other words, our rank is full. Sweet. Alright, so that takes care of the case of the rank hitting one of its upper values of the number of columns. Well, what happens if our rank hits the other possible upper value, the number of rows? Alright, well, spoilers. The rank equaling the number of rows can only happen if ax equals b is always consistent. No matter what value of b you pick, no matter which element of Rm we choose, ax equals b is always consistent. So it always has a solution, so you can always find an x so that a times x is equal to b. Alright, so note the connection here. Full rank guarantees that those systems that are consistent have unique answers. The rank equaling the number of rows gives us something similar. It's in the sense that all systems associated with the matrix A are consistent. So, kind of similar, but a little different, right? Full rank says consistent systems have unique answers. Rank being the number of rows says every system is consistent. And the proof of this is a little bit uneventful in the sense that really the key ingredient is to remember that the column space lives in Rm. And if the column space's dimension is m, so if its rank is m, the number of rows, well, then the column space has to be all of Rm, and so we know the column space are the elements so that the systems are consistent. So every system has to be consistent. And vice versa, if every system is consistent, then the column space is Rm. Thus, its dimension is m, and its rank is the number of rows. Alright, so that's not a particularly exciting proof. It's really basically just hinges on, hey, remember where the column space lives. Well, then yeah, if its dimension is behaving, then it is all of R of m, and so all the systems are consistent. Right? And if you let our mind float back to when we talked about the fundamental subspaces of a matrix, we kind of noted that, hey, we really want the column space to be all of Rm. That means your systems are consistent, which we have now explicitly noted here. Alright, so an interesting thing to look at now is, well, note we've been working with rectangular matrices. Well, when a matrix is square, full rank is the same thing as saying that the rank is the number of rows. So let's go ahead and combine the previous results and state them for square matrices. Alright, so if you have a full rank square matrix, then every system is consistent, and furthermore the answers must be unique. So we always have unique answers in the case of a full rank square matrix. Hey, and that kind of again reveals why we really care about the square case of a matrix. And again, we note that just sort of from intuition, that means that you've got the same number of equations and as the number of variables. So you have enough equations and enough variables. All right. Cool. And here we see being full rank guarantees unique answers in that situation. Not only are our answers always accessible to us, they are always unique. The reverse, though, and this is kind of nice, that for square matrices, to detect full rank, you actually only need to show that answers exist. Which is kind of nice. So full rank has enough power to guarantee unique solutions, but if you want to get the full rank, you actually only need to show that every system is consistent. Alright, let's unpack those two results. So let's start off with, let's suppose we got full rank. Alright, take an element out of Rn. Okay. Well, the rank is full, which means it's the number of columns, but note, in this case, it's also equal to the number of rows. And as we just noted, that means that there is some y, so that a times y is b. but that would mean that B lives in the column space. And now since A is full rank, then any element of the column space has a unique solution associated with it. Nailed it. Alright, so a full rank square matrix, AX equals B, always has a unique answer, and again, being full rank, we know means that your columns are linearly independent, so we are invertible, so we actually already know what the answer to X is, it's A inverse B. Alright, but now if our context of dimension theory helping us out, we kind of have a way of directly speaking of that, so that's kind of cool. Alright, and the reverse, suppose that every system is consistent for a square matrix, then the matrix has to have full rank, because if every system is consistent, then the rank is the number of rows, which means it's the number of columns, because we have a square matrix, so you got full rank. Nice. Okay, so equipped with all of this wonderful information, we can now fully characterize the behavior of any system of linear equations, and sort of in a much more formal fashion than before. So we've already talked about dealing with systems of linear equations directly, and what their behavior is going to be like. But now we see that with dimension at our disposal, the three situations of no answer, unique answer, and infinitely many, we can be very explicit about how that goes down. Right. So if I have a matrix A and a vector B, then three things can happen. If B is not in the column space, then there are no x's, so that AX equals B. So in other words, that associated system for A and B is inconsistent. It has no answers. Alright, well, suppose that we are in the column space and our matrix has full rank. Well, as we just demonstrated, that means there is a unique solution. So there is exactly one. And then the third possibility, well, we are in the column space, we don't have full rank. Well, if we don't have full rank, then if we let H equal n minus the rank, note that would give me that H is the dimension of our nullity, and in that case you can find a basis for your null space consisting of H elements. And then for any x, so that ax is equal to b, so any solution you have now, since b is in the column space, we know there is a answer, a sub p, a times p equaling b. Alright, well, any answer you've got would then satisfy a times x minus p is 0, which would mean x minus p is in the null space, so it's some linear combination of this basis for the null space, then add the p over, and we get that every solution is a linear combination of the L basis for your null space and some particular answer. And hey, when we solved systems before and got them in their parametric vector form, that's exactly what they looked like. So, before when we were directly solving systems of linear equations, we kind of noted that the behavior of the answers kind of end up in this form, and here we see the ingredients, right? The V1, the VH, the things that have the scalars associated with it, are in fact a basis for the null space, and the extra vector we always found was just some particular answer. Right. Hey, pretty cool. And for the differential equations people, oh look, solution to the homogeneous plus the particular? Oh boy. Would you look at that. Wonder if that always happens. Indeed it does. Pretty cool. Alright, nice. So, that's pretty great. And note something a little interesting here. The basis for the null space, n minus the rank, gave us that. Note that these things are essentially corresponding to, right, our free variables. So, if this is our free variables, and n minus the rank is giving us essentially the number of free variables, then hey, wouldn't that mean the rank has to be the number of pivot columns? Yes, it does. So let's actually go through a method of computing that. So indeed, we are about to demonstrate that the rank of a matrix can be computed by finding the number of pivot columns. Again, I went on my little rant of the definition of rank is the dimension of the column space, but the way you compute it is by finding your pivot columns. Right. Do not take the definition of rank to be that is its computation. Alright, so that's what we're going to prove, and note that I kind of already let it slip. You can sort of directly get that result from this statement right here. But we're going to have a much more direct way of proving it, and along the way we're going to prove a pretty strong result, which is that the dimension of the column space coincides with something. But first, let's go ahead and point out that row equivalent matrices have the same rank. That's a pretty powerful tool, and note that that's hopefully not too shocking, again, based on kind of already kind of letting it slip that the rank is going to be dependent on, is going to equal, not dependent, it's going to equal the number of pivot columns. So row equivalent matrices having the same rank isn't too shocking, but what's interesting about the proof of that is that the rank of our matrix, remember, is the dimension of the column space. And as we already noted, row operations will scramble your column space. However, it won't change the dimension. And the reasoning for that is, as we've already previously noted, row equivalent matrices have the same null space. And by the rank nullity theorem, that would mean that the rank of A plus the nullity of A has to equal the number of columns, and that's true for the matrix B as well. But the nullity of B is the same thing as the nullity of A, so those cancel and give me that the rank of A is equal to the rank of B. Hey, the rank nullity theorem doing us a solid with that. Alright, so that reveals that if I've got a matrix and it's row equivalent to another one, the rank is unchanged. So obviously, if I were to go to the ref of A, it'd be really great if computing the rank of a ref matrix was super easy. And again, we've already let slip what it's going to be, but how do you really prove that? Well, it turns out that the key ingredient to getting that is to prove that the dimension of the row space of a matrix is in fact equal to its rank. And you might hear this result stated as row rank is equal to column rank. Anyway, first step is to actually prove the inequality. So we're going to prove that the rank of our matrix does not exceed the dimension of our row space. Right. And I love the proof of this. So the proof of this here that I got here is a little different than kind of how our book approaches this. My proof is I found this somewhere. I forgot. I think I was just Googling, like, how do you prove row rank and column rank are equal? And there's some paper that I found, and this paper has this argument, like, oh yeah, this is super easy. This is all you do. And this is such a cool proof. In the sense that, like, it is a little magic, but, like, all of the steps are, like, really kind of obvious. But it's one of those proofs where it's like, if you had the right idea to begin with, you could probably figure this out on your own, but let's kind of go through it. Alright, so I want to prove that the dimension of the row space exceeds the dimension of the column space, or is no bigger. Alright, well, fix a basis for the row space. Alright. Well, each row then is a linear combination of each one of these, so, hey, we've kind of already pulled this move before where a vector lives in a span, and we've got a list of vectors, and so we'll get a list of linear combos, which means we have a secret matrix. Right, that's exactly how the proof of the dimension theorem went down. Okay, so, hey, I now have these coefficients, so I've got a secret matrix C that I can create. Now note the dimension of C, there's one for each row, so the rows of C match the rows of A. However, the columns of C are a little different, because they're only going up to P, which is the dimension of the row space. Alright, well, the basis elements, I can smush them together. Note I have P of them. And create a matrix. So note the matrix would be a P by N, because these things live where? They live in the row space of our matrix, and each element of our row space has N things in it. Alright, well, if you let C be the matrix formed by the coefficients, and we let B be the matrix by smashing these columns together, well, that means each row of A is just a linear combo of the excuse me, the rows here of B, right? Because if we look at the JKF entry of A, well, we've got our beautiful linear combo here. Well, all right. Unpack what the Kf entry of all of this would be. It would be the Kf entry of our B's, and each one of those, right, that's giving me the, the rows, the Kf column of B, right? No, this is the linear combination of the columns of B, so A time C times B is going to have to equal A. All right, in here we have the nice index management proof of looking at the JKF entry of A and showing it matches the JKF entry of C times B. But again, it's kind of hopefully immediately obvious from this that the rows of A are these linear combos. These are the columns of B. So, hey, it's got to be the appropriate dot products. So the entries of A are in fact the entries of C times B. All right, how does this help me, though, right? Because right now you're kind of like, all right, well, sure, all of this is true. You can write all of this out, but note, we're done. The proof's literally over. But why? All right, well, look at the kth column of A. Where does the kth column of A live? Well, A is equal to C times B, so its kth column is C times the kth column of B, but you've got matrix times vector, which means you've got a linear combination of the columns of C. So the column space of A lives in the span of the columns of C. What's the dimension of our column space? It's our rank. And note, it lives in a span of P elements. So the rank of our matrix, which is the dimension of our column space, can exceed P. The column space lives in the span of a list of P elements, and P is precisely the dimension of the row space. Proof over. Really, what a proof, right? What a slick little thing, right? Like I said, before we got into this, proof is magic, right? It's basically I just create a couple of matrices out of thin air, and they are just the exact right ones to get me the inequality I want. Right, note, using the dimension theorem again, good thing we proved that. Alright, and here we see that the rank does not exceed the dimension of the row space. Now, how do I get the equality, right? I'm claiming that these are actually the same, but right now I just have the inequality. Well, the equality is going to be pretty easy, which we'll now prove, because we're going to pull a little trickaroo. So we know that the rank does not exceed the dimension of the row space, so now we need to get that the dimension of the row space is less or equal to the rank. Well, recall the row space is equal to the column space of A transpose. So that means we've got the rank of A transpose, but by our previous proposition, we know this does not exceed the dimension of the row space of A transpose. But the row space of A transpose is the column space, which is equal to the rank. There we go, we got our equality. Sweet. And note, in the middle of this, we also prove the following. The rank of a matrix is equal to the rank of its transpose. Transposing does not affect rank, which is kind of a pretty wild result when you really think of that. Right, but again, as we've already demonstrated, the row space and the column space must have the same dimension. So, alright, well, yeah, then rank is unchanged by transposing. Right, but really just think about, like, the dimension of your column space transposing not affecting is kind of an interesting thing. Alright, cool. Alright, so, again, recall what we're trying to aim for. We're trying to aim for a computational method for computing rank. Alright, well, we've now demonstrated that rank is actually equal to the dimension of your row space. And it just so happens that the non-zero rows of a row-reduced echelon form matrix are going to form a basis for the row space. Oh, hey. And that's actually really easy to sort of see. We'll take your non-zero rows. We're in reduced echelon form, so anything past the non-zero rows is equal to 0, so the row space must actually be the span of the non-zero rows. So we've got that part down, but now we just need the linear independence. We'll scale and add them up and set it equal to 0. Alright, well, A is in reduced echelon form, which means that if I go to the first row, and if there is a first non-zero element, the leading coefficient, and we know something in reduced echelon form, if you have your leading coefficient, then any row below it is going to have an entry of 0, right? Otherwise it wouldn't be in reduced echelon form. So that means when I plug k into this formula right here, everything except for the first term is going to 0 out, and this will be non-zero, and that will then force alpha 1 equals 0. And then you just go down the rows, and right, because we are in reduced echelon form, all of those things are going to zero out, and so they're going to have to be linearly independent. Cool. You'll get all the coefficients equal to 0. All right, so if you have a ref matrix, then its non-zero rows are a basis for its row space, and that's all we need now, because now we can prove that the rank is indeed equal to the number of pivot columns, as promised. All right, so how does that proof go down? Well, we already have all the ingredients. So let B be the ref of A. All right, well, we know that row operations don't change rank, so the ref of A's rank is equal to the original rank. All right, well, rank is equal to the dimension of the row space, as we just previously proved. And the previous proposition ensures that the non-zero rows of B are a basis for the row space, so the number of non-zero rows is precisely the dimension of the row space. All right, so that means the dimension, the number of non-zero rows of our ref is the dimension of the row space, which means it's the rank of B, which is the rank of our original matrix. But as we know, the non-zero rows correspond precisely to the pivot columns. And there you go. So each non-zero row gives you a pivot column, and yeah, there you go. Ranks equal to the number of pivot columns, as promised. All right, so for example, let's actually do a matrix today. It's been very theoretical, so let's be a little bit more concrete. All right, here's a 3 by 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Its ref is as follows: 1, 0, negative 1, negative 2, 0, 1, 2, 3, and then 0, 0, 0, 0. All right, so note the non-zero rows here. There are 2 of them, and there are precisely 2 pivot columns. And there you go. This our matrix here indeed has rank 2. Beautiful. Now, note something about this matrix. You can go even further. Its rank is 2. What's its nullity? Well, there are 4 columns, right? Rank is 2. Nullity has to add up with rank to the number of columns, so this matrix also has a nullity of 2. So the dimension of the null space of this is 2. Pretty cool. Hey, sweet. All right, and there you go. Consequences of the rank nullity theorem. Beautiful. So we've now proven a bunch of exciting things, and we've got, note, systems of linear equations, their solutions, on lockdown now. We have, exactly what they are, and how they behave. The no answer, unique answer, infinitely many, and we've got a clear picture of how that works. And now, computation of rank, we know how to do it. It's the number of pivot columns. Good stuff. All right. Pretty good. So what's next? Well, next up is time for us to determine it. So that's what we'll do.